So our course is called Introduction to Bosonic String Theory. And my name is Dmитрий Bыкov. Okay, so this course is kind of, we have here a combination of several groups, right? I think a Russian group, an international group. So this course will be in English for everyone. And we have about, I think, 12 to 14 lectures. So we'll finish sometime in December, I guess. There are also some gaps, some lectures. Like next week there will be no lecture, and also in October I think there will be one class will be skipped. Okay, so just some organizational remarks. So first of all, I'd like to have some lists of the groups. So I have the list of the international group, but as regards the Russian group, could someone please send me the list of the group? Yeah, later, please. Yes. And also the international group. Do you have some kind of group leader or something like this who I can be in touch with or something?
I can do it.
Okay, so could you just send me an email, just saying hi or something? And I will write the email. Yes, you can also write me emails if you want. We have these lectures once a week, and as well as some seminar tutorials led by Slava Krivorol, right? I think you had already one tutorial today, maybe. I don't know about the grading of this course. I think you have to formally you have kind of two exams, one for theory and one for these tutorials. Yeah, seminars. So I guess, the grade for the, formally I have to grade both of them, but I guess the grade for the tutorials will mostly depend on how you perform in the tutorials. So please hand in the homework to Slava and so on. Make sure he's happy. So he's happy means I'm happy, means you're happy ultimately. So, okay. And this course, there will be some exam for this course as well. Okay, there are some more people coming. All right. Okay, so let's go to the program of the course now then. String theory is kind of a vast subject, right? And basically endless subject. And has many facets. It's about maybe 60 years old or something like that. So it has developed into a huge area. So this course only covers like a tiny piece of that area. And it's mostly restricted to the, as it says here, to bosonic string theory. And also to just the description of a string moving in flat space. So bosonic string in flat space. So this is a bosonic flat space. So as we shall see, the fact that it's flat space has important consequences, namely that from the point of view of quantum field theory, this is a two-dimensional quantum field theory, the 2D essentially free quantum field theory. And nevertheless, it's somehow using this free two-dimensional quantum field theory, one can describe interactions in higher dimensional space, interactions of particles in higher dimensional space. This will ultimately lead to some interacting in higher dimensional space, which will always be, like I said, flat space, so Minkowski space, 1, d minus 1. And that's kind of the key feature of this theory, if you like, or of this approach. So it's an approach to particles in higher dimensions via two-dimensional field theory. That's the key thing that we'll be studying. But I mean, it will be clear later. But it's good to have to keep this in mind from the start, because this is somewhat unusual, I guess. So the program is as follows. I mean, the topics that we will cover, roughly speaking, are as follows. So this is the first. We will start with the point particle. So this is the point particle. So this is a like precursor to the string. So the string is some extended object that you can think as looks like a loop if it's a closed string. So if you shrink that loop to a point, then you get a point particle, right? So this is this is string. This is point particle. So that's why it makes sense to start with a point particle. And from the point of view of the formalism, that means that in place of two-dimensional field theory, we have one-dimensional field theory. So from 2D, one goes to 1D, which is therefore mechanics or quantum mechanics. So this is why we'll be starting with a point particle. Then we pass to relativistic string. So relativistic roughly means that it's in Minkowski space, not just in n-dimensional Euclidean space, but in Minkowski space. And here the main concepts are the Nambu-Goto action, and what is called a Polyakov action. So this we will compare the two. So Nambu-Goto versus Polyakov action. Yes, maybe I should mention, since I mentioned that there will be some kind of field theory and mechanics, quantum mechanics, etc. So there are some prerequisites, right, for this course. So I mean, I hope you're familiar with some topics from the start. So these are classical mechanics, such as Hamiltonian formalism mostly. Then quantum mechanics. And some aspects of quantum field theory. So quantum field theory will not maybe need that much from quantum field theory. I mean, just some basics. Mostly free fields, yeah, so free fields. Free fields and a bit of renormalization. So these are the things that one should ideally be familiar with. Okay, then, so point particle relativistic string. Then we have the spectrum of, well, the free string, so free string, or spectrum of free string in flat space. So this is a quantum spectrum. And we will discuss how the spectrum is obtained in two different ways. Yes, so the two different ways are called the light cone gauge and the conformal gauge. So the light cone gauge and conformal gauge. Where, in particular in the conformal gauge, we'll have some, well, the aspects that we'll discuss include the Virasoro algebra, Virasoro constraints, or algebra of Virasoro constraints, and what is known as the Weil anomaly. And critical dimension. Okay, this is so this is the spectrum of this free string in Minkowski space. I mean, point 3. But then we'll discuss interactions, string interactions. So that means interactions of the particles described by this string theory. And for that, we need what is called vertex operators. That ultimately leads to simplest scattering amplitudes. So more exactly, the most famous of this is the so-called Veneziano amplitude. I mean, that's the most famous and simplest one. So we will derive it in this formalism. And actually, we will start by discussing it even today. Because historically, this was the start of string theory with the proposal of the Veneziano amplitude. I mean, Veneziano is a name, okay? Like, so. So this amplitude first was kind of proposed by some kind of intuition or insight, and then it can be subsequently derived in the framework of this whole machinery of two-dimensional field theory, which is the string theory that we're discussing in this course. So then there is a slightly topic that stands somewhat separately, but it's also useful to understand it or have an idea about it, which is usually in textbooks is called something like effective actions. Effective actions. So these are the in, so that means effective actions of fields in the space where strings live. So ultimately, we'll see that these strings, they are like an infinite collection of particles. You can think of them as an infinite collection of particles, each particle corresponding to some field, like you have in field theory, quantum field theory. And for each field, you can write some Lagrangian, right? So this Lagrangian, or this action, is called effective action. And of course, they, in principle, interact with each other. So it should be an interacting Lagrangian. And there is some extra way, additional way of deriving these effective actions via computing beta functions. So-called beta functions. Which have to do with exactly the renormalization of your in the interacting to Z theory. So most of what we will be studying has to do with free field theory in 2 dimensions. But in free field theory, you have no renormalization, or you don't need renormalization. But at the end, we'll see that it's also kind of useful to study what is called strings in curved space. And this leads to interacting quantum field theory and to renormalization in interacting quantum field theory. And that's related to the interacting field theory in target space, what is called target space, so in the Minkowski space. So it should look like a kind of mixture of various things, because you have 2-dimensional theory and you have theory in R1, D-1. And you both have free and interacting theories in both cases. So they're all somehow related, so via all these topics. And I mean, this relation is basically what is called string theory, or at least these aspects of string theory that we will be studying. So, now I'll mention some literature that you can use. So the literature is, again, the literature is quite vast on string theory. There are lots of books, and these books are typically quite thick. So you'd have to choose some parts of those books, or the books that you like most. But I'll just mention first some kind of classic references. One is Green, Schwarz, Witten. Called superstring theory. Again, it has, I think, two volumes, but we will only need chapters 1-3, which discusses free strings, and chapter 7 it discusses 3 amplitudes. Then Polchinski, the second book. Polchinski, string theory. Again, volume 1. So this is mostly deals with conformal gauge and CFT methods. So conformal field theory methods. And so superstring theory is some kind of another important refinement of string theory. So we're dealing with bosonic string theory. That means most of the fields we'll be dealing with are bosonic, kind of commuting fields. And there's some refinement that adds on top of that some additional anti-commuting fields, which are in physics language are fermions or superpartners. There is has something to do with supersymmetry and so on. And it's kind of an important refinement, but I think it's in some other course. It's covered in some other course, the one that was on the board here before. Okay, and then there's a book, Blumenhagen, Lust, and Tyson, Basic Concepts of String Theory. And here we need the first, so chapters 1 to 6. So this is a little bit more modern or updated book as compared to these ones, which are quite old. And it's more or less covers, I think, the things covered here plus maybe more things. So these are proper books, which are quite thick, like I said. And maybe you will find it sometimes more useful to deal with some lecture notes, because there are also various lecture notes available on the internet. So I'll now mention those lecture notes. So I think maybe the one that will be most closely related to this course, or this course is most closely related to that one, is the so some lecture notes. Is, by Townsend, called String Theory. I think this may be the most readable course, and probably very close to what I'm going to be talking about. So I hope you can find it on the internet, because if you don't find it, I can post it on those Telegram group or something like that. So let me know later. And there's also a course by Arutunov, lectures, string theory, and also lecture notes by Toft. Introduction to so Toft, he's actually Nobel Prize winner, kind of very famous particle physicist and so on. Okay, and yeah, you can also find various lecture courses on the internet, I mean videos and so on. So now we'll have an extra video. There will be an extra one after this course is recorded, I guess. Okay, and then there are more popular accounts of some more popular accounts about string theory. Is popular, kind of quotation marks, but it's less rigorous, maybe without derivations and so on. They just give you some results, but it's useful because it kind of presents you the final results pretty fast. So so one is Becker Schwartz. String theory and amp theory. And also the lecture notes by Tong. Some Cambridge lecture series, also called String Theory. And finally, there is a nice historical book about the developments, like historical developments around string theory, starting from the 60s. It's called The Birth of String Theory by theory. So these are, that's it about the literature. So maybe, like I say, maybe these lecture notes are the closest to what I will be talking about. And maybe if you want to read a book, then maybe this book is might be most relevant. Okay, so that's it regarding literature, various formal aspects. Okay, so now we'll come to the first, like say, historically first result on string theory, which is the Veneziano formula. And so this is, so we'll start from the end of the course. Kind of, this is historical development, as you can, you might call it just discussion of the historical development. Where string theory came from. So this is the Veneziano formula for a scattering amplitude. So it's a formula for a scattering amplitude. And so back in the 60s, so this is from 1968. So people were studying strong interactions, so hadronic interactions, and because they're strong, so they don't have any kind of small parameter that you can expand, with respect to which you could make an perturbative expansion. So it's a kind of complicated theory, and there were some experimental data on the scatterings of mesons and hadrons and so on. So the particles participating in strong interactions, and the attempt was to find some kind of theoretical explanation of those scattering amplitudes. So strong interactions. So these are mesons and hadrons. So, for example, some examples of those mesons are the pi mesons, say pi plus, pi minus, pi 0. Somehow Veneziano proposed like an empirical formula, so a formula that he came up with that described well the observed scattering amplitudes of these mesons at high energies, which is called the Veneziano formula. So this is so high energy scattering, you could say. So there were as well some approximate theories describing low energy scattering. So for low energy scattering, there was some low energy scattering. There were also some approaches as to how one can describe low energy scattering via so-called effective pion Lagrangians. Pion nucleon Lagrangians. And here the keywords are sigma models, and chiral symmetry breaking. And this is nicely reviewed in the book of Steven Weinberg. So quantum field theory. So if you're, so this is a rather beautiful topic that based on just some symmetry properties, one can derive effective theories describing low energy scatterings of, say, pions. This was also called, sometimes it's called current-to-current algebras, etc. So this was a topic actively investigated in the 60s. But as regards the high energy scattering, the formula proposed by Veneziano has the following form. So it's a formula for some amplitude, which is roughly looks as follows. So there are two particles colliding and two particles going out after the collision. So with momenta K1, K2, K3, K4, right? So we have, of course, momentum. So there's something happening here, some interaction of these two particles. And of course, there is conservation of momentum. So there is K1 plus K2 plus K3 plus K4. So the formula looks as follows. So A of S and T is gamma of T alpha of S of alpha of T. Okay, so what are these things entering this formula? So first S and T are the Mandelstam variables, right? So S is K1 plus K2 squared. T is K3 minus K1 squared. These are Mandelstam variables. Again, these are all names coming from names of people, so there's no other explanation for these names. Well, these are the Lorentz invariant combinations, right, that you can build out of these four vectors, four momentum vectors, right? So in yeah, so here it's assumed that the each k I squared is minus m squared minus mi squared, right? So the masses of the particles are fixed, so the square of the momentum. So this is in Lorentzian signature. So this is a scalar product in indefinite signature. So that's why minus makes sense. Okay. Yeah, maybe I should say that. I mean, this is Minkowski space. So we're dealing with Minkowski space with signature minus 1, 1, 1. Here, I mean, of course, the real physical space is 3 plus 1 dimensional, but in string theory, we also allow for kind of an arbitrary dimension to start with that I call D. So once you fix the absolute values of the momenta, then the only, and impose the momentum conservation constraint, the only Lorentz invariant combinations that are left are just S and T. Sometimes one also uses the U variable, which is the difference between, say, K4 and K1, but the sum of those S, T, and U is fixed. So the independent ones are only S and T. So since we are dealing with Lorentz invariant field theory, our amplitude should be Lorentz invariant, so it should be expressible in terms of S and T. And the question is what the expression is. So the Veneziano formula is this formula here. So gamma is the gamma function, just the Euler gamma function, the one that's related to the factorial. Alpha of S is some function, some linear function of S. So alpha of S is alpha 0 plus alpha prime S times S. So this is for reasons that will become clear later. This is called a linear Regge trajectory. Regge trajectory. Again, this is a name of a person. So, and I mean, these Regge trajectories, they are kind of a key concept in this course. So it's good to start getting used to them from the start. So this alpha 0 is sometimes called the intercept of the Regge trajectory, and alpha prime is the slope. Okay, and so we'll now take a small break, but just before the break, I want to mention that this formula is a tree-level approximation. So this is a tree-level formula for tree-level scattering. Tree-level scattering. So you know, in quantum field theory, there is an expansion in the number of loops. So first there is 0 loops, which is called tree level. Then there is 1 loop, 2 loop, etc. So tree level means that this amplitude, you can actually make this amplitude more concrete. So it's not just an arbitrary thing inside this disk, but this is actually a sum over kind of this, so these types of Feynman diagrams. So this is a typical 4-point tree-level scattering amplitude, right, in quantum field theory, where we assume that the vertices are cubic. Let's assume for simplicity that they are cubic. So there are only cubic interactions. So these are the original particles that we had in the picture. And the particle here is some particle being exchanged. So this is some particle being exchanged. Of mass mi, or let's say ma and spin sa. And then we sum over all possible particles that we can exchange here. So this is sum over A. Okay. So I'm saying here we're considering just an imaginary kind of quantum field theory where our original particles are interacting with some intermediate particles, but there can be an indefinite number of these intermediate particles. And the claim is that if you allow for this kind of interactions, you can in principle reproduce this type of amplitude. And we will see why. And the important point is that this set of variables with respect to which we sum, so the set of particles is actually infinite. So we sum over infinitely many particles. So this is an infinite set. So the point is that there is no way to reproduce this amplitude by finite number of particles. And ultimately, these infinitely many particles are kind of nicely predicted or described by the string theory formalism. If you look at it from the point of view of field theory formalism, you have to think of an infinite number of particles arising from somewhere. And so after the break, we'll describe in more detail how to derive this amplitude starting from Veneziano amplitude. Okay, so let's analyze this formula. So that's our main goal is to analyze this formula. So this formula had historically several important features. So it gave some so phenomenologically important behavior in what was called Regge domain. So Regge domain. So that's some kinematical region where S goes to infinity with T fixed. So you can, by studying this S and T, you can find that this corresponds to scattering in some small angles. Because S is roughly the energy in the center of mass frame squared, and T roughly characterizes the angle, the scattering angle. So the behavior of this amplitude is power-like, so it's S to the alpha of T, where alpha of T is this linear function. I think this was one of your tasks in the problem session, so you can just derive it from behavior of the gamma function. And the second property of this formula that we will now discuss more closely is that it gives expansion in resonances which corresponds to Regge trajectories. Which was also kind of an observed phenomenon, the existence of Regge trajectories.
Excuse me?
Mm-hmm.
What is a Regge trajectory?
Yes, we'll come to that. Yeah, it's a It's a way of kind of classifying particles that participate in the strong interactions. So some particles, they lie on some trajectories, some straight lines in some on some plot that we will discuss. Yes. On the other hand, these Regge trajectories, which I haven't defined so far, but just good to get used to the name, they arise from quantization of strings. So quantization of strings. So which is ultimately the reason why this formula appears in string theory. I mean the Veneziano formula. And we'll see that later on. So this is just an introduction. The question is: so there is this formula for the scattering of two particles into two particles. What can we learn about the spectrum of our theory looking at this formula? And as I mentioned here, well, how can you address this question? Well, basically you imagine the scattering goes via this kind of Feynman diagrams, right? So then the various particles of your theory are exchanged in this intermediate channel. So particles of various masses. And so how can you find the masses of these particles starting from the scattering amplitude? So I mean, just very naively, so you have some particles colliding on a collider, and you want to discover new particles. How do you discover new particles? What do you look for? I mean, what?
By testing the conservation of energy.
Okay, yeah, that's one way, yes. But I mean, even that's like some particles that that are weakly interacting or something like that. But I mean, even more naively, like I just look at the scattering amplitude. What can I see on the scattering amplitude? Like some trace of particles in the scattering amplitude of other particles.
Spin.
Well, somehow you can also read off the spin. But I mean, just you look at a plot. So a plot, I don't know, some decaying plot maybe or something like that.
Some resonance.
Yeah, exactly. So there can be some resonances, right, in the plot, some kind of spikes corresponding to the energies corresponding to the energies that are equal to the masses of the particles, right? That because you can produce like many particles of that type when energy is in that domain, right? And so how do these resonances manifest themselves in the formula? What does this imply from the point of view of the formula, of the quantum field theory formula? You have a quantum field theory, you calculate a 3-level amplitude. Divergence, yes. Well, that's right. So more exactly, there are some poles. So the amplitude can have some poles, the 3-level amplitude can have some poles as functions of the energy. So the energy here is S. It's at least conventional way of denoting the energy squared, right, in the center of mass frame. So we'll be looking at this at the poles of this guy as function of S. And usually in 3-level quantum field theory, we don't have any more complicated singularities than poles, right? Just because do you remember how the propagator typically looks like of a scalar field? I mean, to each internal line there corresponds a propagator, right? And which, if there is momentum, so this is K1, K2. So here there is momentum K1 plus K2. So it looks like 1 over K1 plus K2 squared plus M squared, right? This is the propagator. So this is 1 over s plus m squared.
Can you explain why plus m squared?
It's related to the signature, right? So I mean the signature is yeah, that's right. So I mean I fixed this mostly positive signature, but maybe sometimes I will choose otherwise. But I hope to be consistent, but I don't promise. So you see there is a pole in S at S equals to minus m squared. And so here we're summing, if we're summing over many such particles, we'll have many poles at various positions of S. And well, what can we say about this guy as a function of S? Where are the poles?
Negative integers,
Huh?
right? Integers to negative.
Yeah, so at the they correspond to poles of the gamma function, which are the negative integers, right? So let's recall the formula for the gamma function. So I hope you remember the formula for the gamma function, which is gamma of z is integral t c minus 1 e to the minus t from 0 to infinity. So so this integral is convergent at 0 for z greater than 0, right? For z positive. What happens when z goes to 0? Well, I mean, z equals 0, there's a divergence, right, at 0. So how do we figure out what divergence this is? I mean, how do we figure out the asymptotic expansion of gamma of z when z goes to 0?
And there's some product expansions like fancy inter-product formulas that make this clear.
No, okay, no fancy stuff, just simple stuff. Let's just looking at this formula. No, I'm sure you can put it. One way is to put it in Mathematica and get your expansion. Yes, that's a fancy way. Taylor expansion.
For the exponential or something like that.
But if you Taylor expand the exponential, then it will be divergent at infinity, right? So I mean, the exponent suppresses this at infinity. So the answer is just integration by parts, yes? So this is 1 over z d of t to the power z, right? And then you integrate by parts. And after you integrate by parts, we don't have an extra t to the minus 1, so it becomes convergent when z goes to 0. And the divergence is in the presence of 1 over z factor, right? So this is a so that means that it's 1 over z plus regular terms when z goes to 0, right? So what about other negative values of z? I mean, this is z equals 0. I mean, non-positive. What about the other ones?
Integrate by parts again, you can find some recursive relation.
Well, yeah. So you use the standard relation for the gamma function, right? The factorial type relation. So gamma of z is z minus 1 times gamma of z minus 1. So now if z goes, for example, to, we want the argument to go to minus 1. Here z goes to 0. Z goes to 0, z goes to 0. So again, we find a pole behavior, right? Pole-like behavior. So iterating this guy, you get z minus 1, etc., z minus n, gamma of z minus n. And then you send z to 0. So you find that gamma of z minus n is of minus 1 to the n over n factorial z. Or if you shift z to z plus n, so gamma of z behaves as minus 1 to the n z plus n as z goes to minus n plus regular terms. Okay. And so now we'd like to expand this amplitude, I mean the gamma function standing in the numerator, the one that's a function of s, into its poles with respect to s, right? Alpha of s is a linear function of s, so it has some poles related to the negative integers, right? So we want to do the following. So we want to expand so we have, say, gamma minus x, gamma minus y to gamma of minus x minus y, right? That's what we have. And let's expand it in poles of y. So here we have poles of this gamma function. So this will be an expansion, n from 0 to infinity, gamma of minus x, gamma of minus x minus n, minus 1 to the n factorial n minus y. So I've just expanded the gamma function into as a sum over poles, taking into account only the residues at those poles. Yes, so I get some kind of sum representation for the gamma function. What is the qualification for this to work? I mean, so you have a meromorphic function, you expand it into its poles. When does that work? I mean, I want to present the function as just sum over its poles, taking into account only the residues. When is correct?
Maybe when there are no essential singularities.
Yeah, so it works when the behavior at infinity is controlled, right? You have to control the behavior at infinity. So, how would you prove this formula? So you take the difference between the gamma function and this series. So this is a function without any poles in the finite domain, right?
So it's a constant. If it's
Decay.
morphing in the whole.
It's a constant if it's, if it's 0 if it's decaying at infinity.
Yes.
So you have to, one additional step, you would have to prove that it's decaying at infinity. So you can take a sum over poles. That means the difference between the original function and the sum over poles is an entire function. But then if it decays at infinity, then the difference is 0. So, and that's the case here. But okay, and now something has simplified, right? So here I've substituted the poles, which is y equals n here. So this guy can be further simplified because this is minus x minus 1 minus x minus 2 minus x minus n, which is minus 1 to the n, x plus 1, x plus n, right? So this is just a polynomial in x. this prefactor is just a polynomial in X of degree n. So what you get here is a sum 0 to infinity x plus 1 divided by n factorial times n minus y. So you see this particular function has this interesting property that it has just simple poles in y, and the residues in those poles are polynomials in x. Right? So this is a kind of very peculiar property. So what does this imply for the amplitude a of st? So just by rewriting that same formula, we get that a of st is minus alpha of t plus 1, etc. alpha of t plus n factorial minus n. And so to find the positions of the poles as functions of S, we set alpha of S. So the resonances are at alpha of S equals n, which means and from 0, 1, etc., which means that S is 1 over alpha prime n minus alpha 0, and this should be m squared. Yes, so I believe there is a swap of signature somewhere. So let's say this is okay, minus this. So this is minus m squared. Yes, so something like that. Yeah. So this is m nth squared. So this is a mass of the nth particle, and n goes from 0 to infinity. Yes. Okay, and so the meaning of this is that we have an exchange of an infinite number of particles with masses whose squares are linearly growing in n. Right? So again, I remind you this picture. So so this is the mn. Here this is the nth particle, and now we've derived the expression for the masses of these particles. If we have postulated the amplitude, but if you agree with postulating this amplitude, then you derive the masses of the particles. So this n has some kind of intrinsic meaning. So n is not just a number from 0 to infinity, but it can be related to the spin of the particle being exchanged. So n is the spin of the particle, spin of intermediate particle. So for the moment, we will not try to define very precisely what we mean by spin, but you can just imagine that this means that, this is Lorentz spin. So that means that the field describing this particle has many indices, roughly as many indices as the spin. So for example, spin 0 is a scalar particle, spin 1 is a like vector particle. So say I don't know, phi, a mu, you know, and let's call it, I don't know, h mu nu, etc. And so you can imagine a particle of spin n as being mu1, mu n. Just naively speaking, just a tensor with n indices. And and these particles here will be scalar particles. So we will assume this is phi, some scalar particles scattering and exchanging tensor particles. Yes, that's what's happening. So this necessarily produces, this has some effect on the amplitude. The reason is that to write this cubic vertex, you have to contract phi with, I mean, this is a scalar particle with this tensor particle, phi mu1 mu n. So there are these, I mean, this is the interaction Lagrangian, right? I'm just kind of very, very roughly speaking. Your cubic vertex means you have an interaction Lagrangian with three factors, so two spinless particles and one particle of spin n. But this has to be Lorentz invariant, so you have to contract these n indices with something, right? And so to do that, you'd have to put some derivatives on, say, these fields. So you put some, say, d mu1, d mu2, etc. Maybe then d mu3, d mu n on phi. So for example, something like this. And okay, I mean, I don't care so much where the indices stand. They have to be, of course, raised and lowered correctly. So, so for example, this kind of Lagrangian will corresponds to an will lead to a scattering of spinless particles by an exchange of a spin n particle. This is just an example of a Lagrangian. Like we don't know what is the Lagrangian, but let's just like kind of imagine. So what will these derivatives? How will these derivatives contribute from the point of view of a scattering amplitude? You see, if there was no derivatives here, all of these were scalar particles, then this guy would be just 1 over k1 plus k2 squared. I mean, not the vertex, but the diagram itself. So I mean, if n is 0, so this would be just 1 over k plus m squared, as we discussed, right? So what will happen if there are additional derivatives in the vertices? What do derivatives look like from the point of view of Feynman rules? Momentum, what?
Particle. So it will be like p to the power n in the numerator.
Yeah, exactly. So when you have derivatives, right, in your Lagrangian, that means from the point of view of Feynman rules corresponding to the vertex, you have additional powers of momenta, right? So say, I don't know, k1, k2, so they will be like k1 mu1, etc., k1 mu2, k1 mu2, etc., k2, etc., mu3. So ultimately, these momenta will, because this has to be Lorentz invariant, the answer has to be Lorentz invariant, right? So they will contract between themselves. So there will be some numerator here, which will depend on S and T again. I mean, if you look at it more carefully, or at least if you take the residue at S goes to minus m squared, this will be some function of t, right? The residue will be a function of t, and you can understand that it will be a polynomial of the corresponding degree, of depending on how many derivatives you had here. So for n greater than 0, this amplitude will be some polynomial of degree n in t divided by this s plus m squared. Right? So, and that's precisely what we find here in the expansion of this Veneziano amplitude. So the interpretation of this is that the particle being exchanged has spin n. So it has mass squared equal proportional to n, roughly speaking, and spin n. So, so this is mass spin n. Spin in this sense that it can be kind of modeled by a field with n indices, let's say. So, so the answer that, well, so what does the Veneziano formula correspond to? So it corresponds to a theory where you have infinitely many particles, say, described by this field phi. So this is phi n, yes, phi n, let's say, of prescribed masses, mn squared, that grow linearly with n, and spin n. So in other words, the spectrum corresponds to the case that the squared masses grow linearly in spin, right? This is the so the plot is as follows. So if J is the spin, this is m squared. Then you have so you have some spin 1, spin 2, spin 3, etc. And then you have some let's say parallel trajectories. So this here is alpha 0, right? And the slope of the trajectory is alpha prime. I mean, I'm just drawing this this plot of mass squared versus n, which is the spin, which I now call n. And so at a given mass squared, there are so the intersections with the integer values of spin are the actual particles. Right? And at a given value of mass squared, there is a I'm drawing it so well, right? Yeah, so there can be particles of various spin. So what we've discussed is the particle of maximal spin. So there could be additional contributions from particles of smaller spin. So this one is called the leading Regge trajectory. And these are the daughter trajectories. I mean, they're all supposed to be parallel, so Sorry if the plot is not that great. So the Regge trajectories are these lines in this plot. They describe kind of families of particles of ever-growing spin and ever-growing mass, such that the mass squared is proportional to the spin. Also, it follows from here that so alpha prime is the slope. So alpha prime, the dimension of alpha prime is 1 over mass squared. And in those applications to strong interactions, so there has to be some mass scale set by this alpha prime, and in strong interactions, so which was the original, like I say, historical development, alpha prime was further 1 over GeV to the power minus 2. So basically that's the interpretation of the Veneziano formula, that there are these infinite families of particles whose so it describes some field theory, would-be field theory with infinitely many particles whose mass squared grows as the spin of these particles. And there can be several families of such particles which sit on distinct trajectories. So that's the Regge trajectory. Yeah? Okay, so then on top of the Veneziano formula, there are various generalizations thereof. And the key point that this behavior is somewhat unusual from the point of view of field theory, right? Because it involves infinitely many particles. So from the point of view of this Lagrangian, cubic Lagrangian, you would have to have infinitely many of those capital phi fields. So it's kind of a field theory with infinitely many particles. So generalizations are the n particle scattering amplitudes. So this was 2 to 2 scattering. You can write n to n scattering. So these were known as Koba-Nielsen amplitudes. In the case of what is known as open strings. So the correct generalizations can be obtained once you know the formalism behind this. So far this was just some kind of funny formula that we discussed. But there's a whole formalism that we will discuss, the two-dimensional sigma model or two-dimensional worldsheet formalism that leads to these formulas naturally. And using that formalism, you can, in principle, write out the generalizations. So Koba-Nielsen, Virasoro-Shapiro. So these are closed strings. You can as well write, you could in principle as well write formulas for the scattering of particles with spin. So here I was telling you that it's, say, phi spinless particles. And then there's a capital phi mu1, mu-n here. But you can as well, all these particles are like on equal footing, right? So you could as well just replace these guys with some capital phi's with mu1, mu-s1, mu1, mu-s2, etc., etc. So you could write formulas for all kinds of scattering of all of these particles on each other. They will be just more complicated because they will involve indices. but it can be done in that formalism. So so this was the original formula from the 60s, but like I say, it was initially designed to describe strong interactions, but soon thereafter it was understood that actually, despite some qualitatively correct properties that it has with these resonances and the high energy behavior, it also has some like mismatches with some properties that do not match the experiment. So actually this formula cannot be really correct. It's only correct in some domains of like for this Regge domain and so on and so forth. So this was kind of the idea of using it for strong interactions was dropped, and rather, but it became clear that it could be used in a completely different application, namely to the description of gravity. So there was a paradigm shift. So kind of forget the strong interactions. So the strong interactions were in the 70s. There was a QCD was put forward, and they were described by QCD. So quantum chromodynamics. So SU3 gauge theory. So this is just SU3 gauge theory. So, but the string, this kind of Veneziano amplitude and string interpretation can be applied to the rather to quantum gravity. So quantum gravity. So quantum gravity plus higher spin fields. So quantum gravity with higher spin fields. So that means that the reason for quantum gravity is that it was found that in the spectrum of the string model, there was of a closed string model, there was a massless particle of spin 2. So there's a closed string gives rise to m squared equals 0 particle of spin 2, which can be interpreted as a graviton. So it corresponds to the kind of space-time metric. So this is graviton. So that means the actual Regge trajectory that appears there, it has a massless particle spin 2. So there's actually some kind of trajectory passing through this point. And alpha prime is has to be modified to match the interactions of quantum gravity. So, or of gravity in general. So alpha prime has to be, in this case, promoted to 10 to the 18th GeV to the power minus 2. So because the kind of the scale of QCD and the scale of gravity are completely different, so this is what is called the Planck mass. So this is the mass scale or length scale that is typical of gravity. Well, the nice feature of this formalism is that in principle it allows you deriving the scattering amplitudes of various particles in this kind of quantum gravity without any infinities. So usual Einstein gravity is a non-renormalizable theory, as you probably know. So if you start computing in Einstein gravity as you do in ordinary quantum field theory, that doesn't work like that. So you have to add like, more and more counter terms and so on. So there will be more and more infinities arising in various loops. So there's a problem with quantization of Einstein's theory that's not present in, say, electrodynamics or QCD or something like that. So gravity is different. And so this string theoretic formalism, it kind of bypasses these difficulties and in principle allows to write out, say, scattering amplitudes, kind of formulas like this straight away without those infinities. And well, I mean, the conceptual explanation is that there are these infinitely many particles of ever increasing masses whose contributions somehow cancel the infinities. So if you had a finite number of particles, you wouldn't be able to do that because it's a non-normalizable theory. But if you add all those infinitely many particles in a particular way prescribed by string theory, then kind of this problem is resolved. But I mean, string theory has its own problems like extra dimensions and so on and so forth. So it's not totally satisfactory model for gravity in the real world, but it's some model of quantum gravity, and that's intrinsically consistent, let's say, somehow. So starting from next time, we will go to the actual one-dimensional or two-dimensional formalism that at the end of the course will allow to derive this kind of scattering amplitudes, explain these Regge trajectories, etc. So yeah, that's it for today.